Okay.
Okay, so our next talk is on putting weak memory in order, and it's by Sung-Hwan Lee. Take it away.
Yeah. Thank you. Good morning. My name is Sung-Hwan Lee, and today I will present our work on developing an in-order memory model with a minimal performance overhead. So possible behaviors of a concurrent program is determined by various compiler and hardware optimizations. A relaxed memory model explains such program behaviors in an abstract way. However, defining a good relaxed memory model has been an open problem for more than 30 years. The challenge stems from the tension between the two requirements, efficiency and usability. Regarding the two requirements, existing models can be divided into two kinds. On the one hand, models like RC11 and Okama memory model meets usability, but they are less efficient, meaning that they do not support important optimizations performed by compilers and hardware. On the other hand, models like promising semantics and request MO are efficient, but fail to meet usability. In particular, we identify that the usability problem arises from out-of-order executions. Let me explain this point in more detail. Recent models that focus on efficiency use out-of-order executions to model weak behaviors due to instruction reorderings. The problem is that out-of-order executions are too complex for programmers, and there are very few verification tools for these models, unlike in-order models for which multiple program logics and model checkers have been developed. Indeed, out-of-order executions are a huge hurdle in modular reasoning. Suppose that I'm reasoning about a library function that I developed. Then I want to reason about my code modularly, ignoring the unknown context code. However, out-of-order executions hinder such modular reasoning, because even when reasoning about my code, I have to consider the early execution of unknown future instructions. Then, the natural question would be, can we model all relaxed behaviors with in-order executions? To do so, we may use other mechanisms that allow us to model relaxed behaviors while keeping the execution of the program in order. For example, store buffers or thread views. Unfortunately, even with these mechanisms, the answer is no. And that's why efficient memory models use out-of-order executions. So, an in-order model should restrict some relaxed behaviors, and thus, these models have performance overheads. However, our results shows that this performance overhead can be made nearly zero. In this work, we develop an in-order model that supports all common compiler optimizations and can be efficiently mapped to hardware with only negligible overhead. All the results of this paper are fully mechanized in the Coq proof assistant. In developing in-order memory model, we target C and C++ languages where memory accesses are divided into two kinds. Typical memory accesses like pointer accesses are non-atomic. For these accesses, data races are not allowed, so programmers should avoid data races using, for example, locks. Also, non-atomic accesses are heavily optimized by compilers. On the other side, atomic accesses are needed for synchronization, and they are usually provided as library functions. Of course, data races are allowed on atomic accesses. And also, no compiler that we know of optimizes atomics. But note that both non-atomics and atomics are optimized by hardware because there is no distinction between the two kinds in hardware. So, because of the differences between the two kinds, we have different challenges and solutions for them. First, I will discuss the challenges and our solution for non-atomic accesses. For non-atomic accesses, in-order memory models can support most optimizations, including instruction reorderings. Roughly speaking, this is possible because when memory accesses are race-free, then the effect of reordering is not externally visible. Let me explain this intuition using a simple example where all instructions of the two threads are protected by a lock. Here, in any execution of this program, one thread should be executed entirely before the other because of the lock. Then, there is no effect of reordering the two instructions of thread 1 because switching instructions 1 and 2 in these executions makes no difference at all. Now, what if we remove log and unlock from the two threads? Then, certainly the effect of out-of-order execution can be observed, but we don't need to consider such programs because racy programs are considered wrong in the first place. Technically, existing in-order models like RC11 define data races to be undefined behavior. Therefore, compilers are allowed to do anything about these programs, about racy programs. So this kind of mechanism is often called catch-fire. The problem is that a catch-fire model cannot support load interaction. Load interaction is an important optimization performed by LLVM and GCC as a part of loop invariant code motion, load widening, and so on. The problem is that introducing a load may introduce a data race which is undefined behavior in a catch-fire model. For example, consider this code that adds x for n times to the variable sum. Both LLVM and GCC optimize this program into a single multiplication. Let's consider when n is 0. Then, this optimization introduces a load from x. Now, suppose that the unknown function foo spawns a thread concurrently writing to x. Then, the read from x races with the write by foo, leading the program to be undefined behavior in a catch-fire model. On the other hand, there is no undefined behavior before the optimization because there is no read from x at all. Therefore, this optimization is unsound in a catch-fire model. To address this issue, LLVM specification follows a natural idea. It considers a racy read to return an undefined value instead of invoking undefined behavior for the whole program. So let's consider an in-order model where a read returns an undefined value when it races with another write. Now, in the previous example, the racy read returns an undefined value without invoking undefined behavior. Then, the sum variable remains 0 since the undefined value multiplied by 0 is 0, and this time the optimization is correct. However, the problem with this approach is that load store reordering becomes unsound. I refer to the paper for the concrete counterexample. So, how can we solve this problem? In this work, we observed that we can have two models, one for the source language, which allows in-order reasoning, and the other for the intermediate representation that allows compiler optimizations. For the source model, we use in-order semantics with undefined behavior for all races, which is amenable to existing verification approaches. For the IR model, we use out-of-order semantics with undefined value for racy reads. Then the IR model validates load store reordering using out-of-order executions, and it also validates load introduction since it does not invoke undefined behavior on races between write and read. To summarize non-atomic parts, we showed that we can have an in-order memory model without any performance overhead in non-atomics. In particular, unlike existing approaches such as RC11 that do not support load introduction, our approach supports all common compiler optimizations. We also proved the correctness of mapping the source model to the IR model and the IR model to ARMv8 architecture. Now, I will move on to the atomic accesses. Unlike non-atomics, data races are allowed for atomic accesses. Therefore, we cannot exploit undefined behavior for modeling relaxed behaviors due to reorderings. Instead, we must reduce relaxed behaviors by restricting optimizations performed by compilers or hardware. First, we do not need to restrict any compiler optimization because no compiler optimizes atomics. The reason is that it is hard to estimate the performance impact of optimizing atomic accesses under contention. Now, I will discuss the restriction on hardware optimizations in the rest of this talk. The only hardware optimization we need to restrict is load store reordering, and it is restricted even rarely. First, other kinds of reorderings can be captured by in-order executions. Moreover, the restriction of load store reordering is only required for relaxed writes, which are much rarer in programs compared to non-atomic writes. Note that no such restriction is required for non-atomic writes, as we allow all optimizations on non-atomics. Now, We need to understand the performance impact of restricting load-store reordering. Among the 4 kinds of reorderings, 3 of them are observed on most CPU implementations of ARM and Power, while load-store reordering is only observed on few ARM CPUs. This is because the performance impact of 3 reorderings in hardware is significant, while the impact of load-store reordering is relatively small. In fact, we consulted ARM engineers and learned why the performance benefit of load-store reordering is so small. To see why, suppose that a CPU core is about to execute a store y equals 1, and the previous load from X is still in progress because it is taking a long time. Now, when the store is executed, it is first to move to a core local store buffer. Then, in the perspective of its own core, the store y equals 1 can be treated as completed before the completion of the previous load. Therefore, the core may execute the later instructions, and the store in the buffer will not block any further execution. At some point, the store will be committed and become visible to other cores. There are 2 approaches to when to commit the store. Specifically, we can either forbid or allow the commit before the completion of the previous load. First, if we forbid the early commit, load store reordering is not visible to other cores. This is what actually happens on most CPUs where load store reordering is never observed. On the other end, we may allow the early commit and then load store reordering becomes visible to other cores. This makes the CPU design more complex, but the early commit has no performance benefit unless the buffer is full. That's why the benefit of load store reordering is small, and only few CPUs perform it. I also note that hardware engineers do not evaluate performance impact of in-core optimizations on concurrent executions. Accordingly, for efficient compilation of an in-order model, we propose strong store instructions that prevent reordering only with previous loads. On most CPUs that do not reorder load and store, a strong store has no performance overhead. Even on few CPUs that do reorder load and store, a strong store can be implemented only with a small performance overhead. Then, we can use strong store to compiling relaxed writes. Crucially, since non-atomic writes are still compiled to plain hardware stores, strong stores are only rarely used. Therefore, the performance overhead is negligible, if any. All in all, we developed an in-order memory model with only negligible overhead. We provided an in-order source model for programmers based on the promise-free fragment of the promise semantics. This model can be efficiently compiled to hardware only with negligible performance overhead. The IR model allows out-of-order executions for non-atomic writes, and it is based on the promise semantics. We also provided a simple sequential model for compiler writers by applying the result of our paper at the last PLDI. Specifically, we proved that a compiler optimization correct under the sequential model is also correct under the IR model. Therefore, programmers as well as compiler writers do not need to understand the complex IR model. In the paper, you can find more details about the 2 models and formal results on them. This is the end of my talk, and thank you for listening.
Yatin Manerkar, University of Michigan. Thank you for the talk. Regarding your claim that no compilers optimize atomics, did you experiment with the IBM XLC++ compiler at all?
Not really.
Okay, because at least one version of that was trying to optimize atomics. So I was just curious whether you looked at it or they had changed their way of going about things. Another small question I had was, I believe you mentioned on a slide that hardware treats atomic and non-atomic operations identically, if I remember correctly. For ISAs with instructions like acquire and release, that's not strictly the case, is it? Or am I misunderstanding what you said?
Yes, you're correct. It's just for presentation, I just mentioned about what I refer to is that relaxed accesses and non-atomic accesses are compiled to plain accesses in the hardware. That's what I meant. And of course, acquire and release accesses will be compiled to different instructions.
Okay. Thank you.
Thank you.
Jean Pichon, Haute Universität. So this low overhead that you were proposing for the atomics, I didn't quite understand. Do you suggest that inserting a fence that prevents this reordering on current hardware is cheap? Or are you suggesting that designing new hardware that forbids this reordering is cheap?
I am suggesting to design new hardware with new kind of instructions that forbid load store reordering in particular, without forbidding store reordering. And yes, forbidding store reordering may be expensive in hardware, and that was kind of our observation. But forbidding load store reordering is not that cheap, that expensive. So what is proposed is that to introduce strong stores that prevents reordering with previous loads, or maybe load store fence that prevents reordering of load and store, and use this to compile the relaxed rights.
Okay, maybe a quick aside. Have you tried inserting the cheapest fence that prevents the reordering on the current hardware that exhibits it, and do you have performance numbers for that?
Well, I don't have performance evaluation in this paper, but personally I tested on concurrent data structures before, and by using release rights or release fences, I kind of observed 1 to 5% of performance degradation.
Okay, that's interesting. Thank you.
Yeah, thank you.
Cool. Okay, let's thank the speaker.